exam. Oh yeah. Oh yeah, we established that last time. Yeah. Hey, so guys, what I'd like to do, let me say, what I think you would like for me to do is to review before we get started. So, guys, last time we talked about this idea that we are entering into a unit where we are studying in greater detail the nuclei of atoms. What's going on inside that little ridiculously dense ball that is in the middle of a nucleus. And guys, if you remember when we did that, we started here, and you don't need to write this down because it's already in your notes. But guys, as we got started, we had this sort of conversation that went, shame on you for never questioning the nucleus. Guys, since you were little, well, since you were probably 8th grade, you were taught that this nucleus is this little bundle of positive charge, and we talked about the idea that the nucleus should not exist. Those positives want to get away from each other, and they shouldn't bundle together as Rutherford proposed, and so we solved that problem by talking about what's called the strong nuclear force. And guys, the strong nuclear force is this force of attraction that overcomes the repulsion of the protons holding the nucleus together, and it's very strong. Then we talked about the idea that when this force fails and a matter is converted into energy, that's what Einstein's equation is all about. And so when we disrupt this strong nuclear force, matter turns into energy, E equals mc squared. That's all the energy of nuclear explosions and fusion and sunlight and all these other nuclear processes. So guys, any questions about strong nuclear force, nuclei, fission, fusion, good there? Okay, then guys, we went on to say this. We said that there are actually two types of nuclear change, and you don't need to write this down. There are strong changes and there are weak, low energy changes. The high energy changes are fission and fusion, and I believe we're done with that. But then guys, we've got the low energy changes, which we call radioactive decay or radioactivity. Now guys, there's 3 types of this that you need to know, and these are then our marching orders for today. So guys, today what we're going to do is we're going to talk about low energy nuclear changes. This is what we call radioactive decay, and this is alpha, beta, and gamma decay. So guys, that is what we're up to today. You guys good? You get the idea where we're going? Okay, then let's get started. So guys, in order to have this conversation, the first thing we need to talk about is decay. So this is where you want to start taking notes. So guys, decay is the breaking down of nuclei. But guys, you've got to understand when we say decay, we are not talking about fission. This is not the strong nuclear force breaking apart and goodbye Hiroshima. Guys, these are low energy changes where the nucleus doesn't break apart. The strong nuclear force is still intact, but still it can leak. So if you want to think of it that way, it's like the nucleus leaking particles. So guys, when that happens, what we end up with is unstable nuclei that are undergoing radioactive decay to become more stable nuclei. Yeah. Hey. I'm gloved up and ready for you. Don't be nervous.
I just barely got it.
All right. So guys, here's where we're at. We understand that there are strong nuclear changes that are fission and fusion, but we can also have these lower energy changes that we call decay or radioactivity. And guys, what's happening is that unstable nuclei are becoming more stable. So guys, in order to understand this, we need to talk about stability. And obviously you can't draw this, but guys, take a look, give it a read, and then we'll talk about it. Start on the left. Read the little blurb there, and actually let me zoom in a little bit. And then we're going to take a look at the right. Uh-oh. So guys, the blurb on the left describes the graph on the right. We're going to talk. And then guys on the right, interpret that graph. What does that thing mean? And now guys, what I want you to do is taking turns, starting with the person that's on this side, the right side of your table groups, your lab partners. The guy on the right or the girl on the right, and if you're alone, you can sort of condense. Guys, the person that's on this side of the table, explain what this graph means to the person on the other side. Explain it. Go. What does this graph mean? Okay, now stop. The person that was not doing the explaining, ask a question of the person that was. An appropriate question is not what did you do for spring break? Keep going. Okay, guys, last thoughts. All right, so guys, let me pull us back together and let's talk about what this thing means. So here's what we've got. Turning our attention to the graph. Guys, let me help you pick this apart. These are skills that you need to have on the ACT, which I am developing a severe hatred for as my children have to take that stupid thing. But guys, one of the things that you've got to be able to do as a part of your background in science is you got to be able to look at graphs and go, what does this mean? Guys, in order to do that, the first thing that you got to do is read the axes. What is the information represented? So what do we have on the x-axis? Protons. So guys, literally, as we move from left to right across that x-axis, literally what we're doing is we are moving across the periodic table, right? Because the number of protons tells us the element. So we are going from element 1 up to element 80. So we're basically marching up to Mercury on the periodic table. So then guys, on the left-hand side, on the y-axis, what do we have there? Numbers of neutrons. Now understand that is not the atomic mass. The atomic mass is the number in red, but that's protons and neutrons. Guys, this is actually just the number of neutrons. So let's take a look. You'll notice that the increments are equal. So guys, what does it mean if we have a line that is going up at a 45-degree angle? What does this 45-degree angle represent? A 1-to-1 ratio, the same number of protons as neutrons. And guys, have you noticed that with the lighter elements, as we've been filling out those tables, they tend to have equal numbers of protons and neutrons? And guys, if you're not sure what I'm talking about, check this out. So guys, for example, boron has an atomic number of 5 and a mass of 10. 6 and 12, 7 and 14, 8 and 16, and so on. So guys, we have equal numbers of protons and neutrons for these lighter elements. And that's what this line represents and what those blue dots represent. Guys, those blue dots are stable nuclei, and down here at the lighter elements, an equal number of protons and neutrons tends to create a stable element. So, now what happens as we get up into the heavier elements? Guys, notice what happens to these blue dots, which are the stable nuclei. They veer away from that 1-to-1 ratio. What does that tell us? More neutrons. Guys, in order for an element to become stable, which means it doesn't break apart, guys, as the atoms get bigger, more massive, we need more neutrons to hold that nucleus together. So eventually we get up here into these super heavy nuclei, and Cam, this is what you mentioned, it's a ratio. As we get into these super heavy nuclei like lead and up in this region, we end up with almost a 1.5-to-1 ratio. So if we've got 80 protons, we've got like 120 neutrons neutrons in that thing, and that's how many neutrons are necessary to make it stable. So as they get heavier, it takes more neutrons to hold them together. So the question is why? And you're going to find out in the video that we watch on Thursday. But guys, the neutrons are there to hold the nucleus together. Does that make sense? Okay, so with that said, guys, I'm now going to throw another question your way, and I'm going to give you a second to talk about it. So guys, the question is this. We're going to call this region 1. That's hard to do with the glove on. And we're going to call this region 2. So guys, what I want you to figure out with the person next to you, thinking about this proton-neutron ratio, guys, what is true of thinking of the proton-neutron ratio, what is true in region 1 and what is true in region 2 relative to that band of stability? Talk about it with the person next to you. So region 1 is below the band of stability, region 2 is above the band of stability. What is true of the proton-neutron ratio? All right, you guys ready to talk? Somebody said the really big answer, and this is where I want to start. Because you totally went off script, you didn't talk about protons and neutrons, but you got to the big picture first, and it is actually in the words off to the left. Guys, what is true of the elements in region 1 and in region 2? They're radioactive. Guys, that's all radioactivity is a nucleus trying to dump protons or dump neutrons in such a way that they can get to this band of stability. So this explains why elements are radioactive. They're trying to get to this band of stability. Some of them do them in one way, some of them do them in another. So now let's talk about the regions. So guys, if we're down here in region 1, which one do we have too many of? Protons or neutrons? We've got too many protons. We've got too many protons. Think of it this way. If we've got a nucleus that's right here, for it to get to the band of stability, it needs more neutrons. To climb up the y-axis, it needs more neutrons to get to the band of stability. Now guys, what about over here? Too many protons or neutrons? Too many neutrons, and that wants to get rid of neutrons in order to get to the band of stability. Does that make sense? Okay, so guys, the question then is this. How do these things either get rid of neutrons or get neutrons, kind of? You're going to see. How do they go about this? And guys, the answer is radioactive decay, and there's 3 types that you need to know. So you guys good on the graph thingy? Okay, so guys, this is the way this is going to go. We are going to talk now. You know what? Do you want to know what kinds of activity they go through? Should I just show you? Okay, so let me ask you this. If I'd asked you to, could you draw that graph?
Yeah. Not the blue dots.
What if you did this? Try this with me, guys. Let's see if this works. You be my guinea pigs. Guys, do this. Draw that. Just do this in your notes. Draw that. Then, guys, down here on the x-axis, put P positive. Over here on the y-axis, put N0. We're going a little off script here, but let's see what happens. Then, guys, draw a line as best you can at a 45-degree angle and put protons equals neutrons. How about that? We okay? Then, guys, you could maybe just draw a squiggle that goes up like that. And that's the band of stability. Is that going okay? Is it a mess or does it look all right? It's all right? So then, guys, let's have this conversation again. If we're below the band of stability, what do we need? More neutrons. And guys, what you're going to find out is the way that that happens is these go through what's called alpha decay. So all of the nuclei below the band of stability will go through alpha decay. And then, guys, up here, we need more protons, and those dudes go through beta decay. Okay, so here's the $11,000 question. What's this going to look like? Is that kind of what yours looks like?
Yeah.
That's not bad. For being a left-handed guy, that's a pretty good drawing. I feel pretty good about it. That's not bad at all. All right. Don't draw the dots. You guys good? All right. So, guys, what we're going to do now is we're going to go through and we're going to dig deeper into how these decays work. So, guys, the first one we're going to talk about is alpha decay. So, alpha decay, which is abbreviated like this. This is actually kind of, sort of, the lowercase Greek letter alpha. But guys, the other way that we're going to draw this, we're going to represent this, is helium 4/2. So let me explain to you what that means, and then we're going to play with this, literally. So guys, when something goes through alpha decay involves the release of a helium nucleus from the nucleus of an atom. So we've got this nuclei, it's unstable, it's trying to get to the band of stability, and the way that it does that is by spitting out a helium nucleus.
So it just sends out helium?
Well, so let's talk about it.
Is it changing elements?
When we talk about a helium nucleus, do I have this print? Now let's do it this way. So guys, find helium on your periodic table. Helium is element number 2, right? What does that tell us about a helium nucleus? 2 protons. Now, this nucleus has a mass of 4. So 2 protons and how many neutrons? Also 2. So guys, this is literally what a helium nucleus is. But how many electrons does it have? None. So what does that make its charge? Positive 2. But guys, you've heard of these before. These are the things that Rutherford shot at the gold foil. Remember? Alpha particles, right? And guys, what do we know about the charge of alpha particles? They're positive. That's why they bent off the nuke. So guys, the idea here is that these are the very particles that Rutherford shot at the gold foil. So kind of bringing it back, you've heard of these before. So this idea of alpha decay involves the release of a helium nuclei, no electrons, so they're positively charged. So guys, literally, this is just 2 protons and 2 neutrons screaming out of the nucleus of an atom. So guys, why did Rutherford choose alpha particles? The answer is this. They are big, and they're fat, and they're slow. Rutherford's thinking was, if alpha particles could get through gold, anything could get through gold. Now understand, when we say big and fat and slow, they're still invisible. These are helium nuclei. They're still bitty teeny small, but on the subatomic world, these are like dump trucks. So, guys, these are big, fat, slow, low energy particles, but they did mostly make it through the gold foil. So do you feel like you understand alpha particles? Okay, so guys, this is what you've got to be able to do with this. Cam brought up a really interesting point, that when a nucleus gives away these alpha particles, we're losing protons, so they become a new element, and you've got to be able to think through that. So guys, what I'm going to do first of all, and write this down with me, I'm going to give you what we call an ROT. That is a rule of thumb. This is the thing when you're studying for the test that you want to memorize so you remember what alpha decay does. So guys, the rule of thumb is this. Z goes down by 2 and A goes down by 4. And then, guys, this is what you've got to be able to do with this. Don't write down the question, but do write down the answer. So, guys, the question is this. What happens to radium-226 when it goes through alpha decay? Don't write down the question, just watch. This is what you've got to be able to do. So, guys, radium is right here. Radium is element number 8, and radium-226 has a mass of 226. You've got to be able to represent what happens to radium-226 when it goes through alpha decay. So here's what you do. Do write this down with me. So guys, write down a big RA. And then let's label it as radium-226. So it's element 88 with a mass of 226. Now guys, here's the question. What does this become when it goes through that kind of decay? So what does radium-226 become when it goes through this kind of decay, which we understand as alpha decay? So guys, to figure it out, do this with me. Draw 3 circles. One underneath the radium, one underneath the line, and one underneath the alpha particle. Now guys, do this. We're going to start on the left. How many protons are in a radium? These are the nuclei of the atoms, by the way. Guys, how many protons are in the nucleus of radium? 88, right? 88 protons. Now, sparing you the math, how many neutrons are in there? 226 minus 88, that's 138. Remember how we said that the essentials for the last unit was filling out the proton, neutron, electron? This is why. Okay, so now guys, what about this? Remind yourself, what is an alpha particle? How many protons? 2. How many neutrons? 2. So guys, that's an alpha particle. So now let's do the subtracting. So guys, if you start with 88 protons and if you lose 2, how many do you have left? Oh, you guys can do math. Now guys, what about this? If you start with 138 neutrons and if you lose 2, how many do you have left? 136. And guys, now we have a new element. This is no longer element 88, radium. This is now element 86, which is what? Radon. And that's a big old Rn. Yeah?
So, if that radioactive decay is happening, is the solvent just turning into a gas?
I'm going to show you. The answer, in this case, yes. This is actually, let's finish this and then let's talk. The answer is scary. So, now guys, this no longer weighs 226. So, 86 plus 136 is 222. Now guys, let's have the aha moment. You ready? Take a look. What happened to the bottom number Z? It went down by 2. What happened to the top number A? Do you get it? Some would call that learning. But let's talk about your question. So when this happens, and it's really neat that you picked this up, when this happens, does this turn into a gas? The answer is not only yes, but the answer frighteningly is yes in Utah County, way too much. So what's going on is that we actually have a fair amount of radium in our ground. It's just present in our soil. And you're absolutely right that when this radium goes through alpha decay, it turns into radon. Now, normally that radon gas just bleeds out into the atmosphere and it's no big deal. But here in Utah County, we dig holes and we put our houses in holes, basements, right? And the problem is that this radon gas can actually get up through the cement of your basement and it collects in your basement and it's actually causes cancer. So a lot of times people will have to suck the air out of their basements to get rid of the radon. Yeah.
My mom actually, she went back and did a radon test because she lived in the basement of her house. It was in Washington.
Yeah.
But she went and did a radon test
Mm-hmm.
and figured out that there's so much radon that she's at like the same risk of lung cancer as someone who's like.
Yeah, isn't that crazy? Yeah, and it's not so. Not only is it a Utah problem, it's a world problem, but it is prevalent here in Utah. And as you're walking through neighborhoods, you'll see that there are houses that have a PVC pipe that comes out of the foundation, and then it turns up to the sky, and then there's like this big bubble in it, which is actually a fan. And then that pipe goes all the way above the roof line, and literally what they're doing is they're sucking the air out of the basement. Mm-hmm. Yeah. Do any of you have radon pumps on your houses? Yeah, once they get that pump in there, it's completely safe. But if that radon gas collects in your basement, it can be a problem. So, do you guys understand alpha decay? Are you feeling good? Okay. So let's follow up on that question though about
why isn't it like a mandatory thing to have those in your houses though?
Because not everybody needs it. And so you can actually go to Walmart and you can buy a radon test kit, and you literally set it out in your basement, let it sit for a day, and frankly, it's weird. It's kind of like a pregnancy test. It turns colors based upon results, and it will tell you whether or not there's radon present in your basement. If it says no, you're good. If it says yes, then you need to bring in the pros that actually have better meters, and they'll measure again and then decide whether you need to evacuate the air out of your basement. So, yeah, but a lot of times this happens when homes sell. The people will say, we won't buy your house until we have it radon tested. So, yeah. Yeah. Happens all the time. Go ahead.
So the radon, the radium, both the radon and the helium turn to gas. The radon doesn't stay solid.
Exactly. So that's exactly what's happening is this solid radium, and it is a solid, is actually turning into radon gas and helium gas. The thing that's really weird is that the majority of the helium gas, like when you fill up a balloon with helium gas, the majority of the helium gas that we have here on Earth is actually created by alpha decay. This is literally the same helium we put in balloons. That's why it's becoming scarce, because the majority of the helium gas that we have here is the result of alpha decay. Isn't that weird? Yeah, it's pretty cool. Yeah, please.
So the radium changes into the gas, right? So does it just like give off so much heat that it just vaporizes itself?
No, that's a great question. And the answer is, so the underlying question behind what you're asking is, why is radon a gas? And the answer we're going to talk about in about 6 weeks, but it's because of its shape. It's so perfectly round that it's not sticky to other radon atoms, and it exists as a gas. You're going to find out that gases tend to be perfectly symmetrical, and therefore they don't stick to other things. So guys, you good on alpha decay? So here's the thing that's interesting. We understand, and I love the conversation, that there's radon and radium and all these different elements around us that are radioactive. Well guys, it turns out the story doesn't stop there. This is actually what's called a Geiger counter. And guys, if you've never encountered one of these before, what you've got is inside this box, and you can actually see it. Well, sort of. There's a tube in here that's full of a gas. And what happens is if radioactive particles, like alpha particles, if alpha particles pass through this, it actually creates a little bit of a charge in the gas. And there's a computer in here that senses the charge and it beeps. So guys, when I turn this on and set it down, let me hold it up so you can hear it. You'll notice that it's beeping. And every time it beeps, it is actually being hit by a radioactive particle. Could be alpha. But guys, every time it beeps, it's being hit by radioactivity. You'll notice that it's not beeping very fast, right? But it is beeping. And what does that mean? We're being hit by radioactivity. So guys, understand, if this tube is this big, imagine if we could replace the tube with you. Guys, you are getting bombarded with radiation every second of every minute of every day of your entire life. But guys, our bodies are amazingly good at shrugging that off and not getting sick. It's not until we have this kind of radioactive exposure that we end up with problems. So guys, have I showed this to you before? So this is uranium. This is actually what uranium looks like when we dig it out of the ground. This is actually from Moab. None of you went to Moab, right? Well, if you drive into Moab, if you've been there before, you may have noticed that off to the right side of the highway, right before you hit the river, there's this big field with all these bulldozers running around. That used to be a uranium mine. Now it's a hazardous waste site, and we're trying to clean it up. But guys, this is the uranium dug straight out of that mine down in Moab. So the yellow is actually the uranium, and then guys, the rest of it is the rock that it's contained in. So guys, right now, this uranium is actually going through alpha decay. So these alpha particles, if you could see them, they're just spitting everywhere in this room. There's alpha particles going everywhere, and every time one hits this, it beeps. And as we get closer, and pretty soon it can't even beep fast enough. And guys, this is what we call full exposure. And every time this thing beeps, and it can't beep quick enough, it is being hit by an alpha particle, and it causes the thing to go off. Do you get the idea? Okay, so now guys, again, check this out. So this is background radiation. This is full exposure. But now listen carefully. So background, beep, there, okay. And full exposure, but now guys watch. Watch and listen. Did you see it? Did you hear it? Guys, watch again. Full exposure, and now this. What's going on? So hold on. So full exposure, and now this. Not getting hit by as much. So guys, let's think about this. We've got alpha particles that are flying out of here. They're hitting this thing. This thing's beeping like crazy. But when I flip my hand over, it slows down. Why would it slow down?
Wait.
Go ahead.
Wait, is it going around or is it
No,
going through?
going through. But here's the trick. You ready for this? The alpha particles aren't. Guys, what do we know about alpha particles? Big and fat and slow, right? That's why Rutherford chose them. And guys, the alpha particles are so big and fat and slow, they can't make it through my hand. So all the alpha particles are actually being absorbed by my flesh, and they can't get through. But is something getting through? How do you know? Because it's faster than background. So guys, this is background, this is full exposure, so this is faster than background, meaning something is getting through. The alpha particles are stuck in my hand, but something is getting through. And guys, what has to be true about this? This is like Dr. Seuss. What has to be true about the something that's getting through? Try it again. Seriously. Well, it's radioactive, but what has to be true of these particles that are getting through my hand? Smaller, faster, high energy, right? And guys, these smaller, faster, high energy particles are actually what we call beta particles. This is actually the lowercase Greek letter b, beta. But this is what a beta particle actually is. What is that? It's an electron. But guys, notice, you're accustomed to writing electron like this. This is not its charge. This is representative of its mass change. We'll talk. You'll see. Okay, so guys, ready? What is a beta particle? Here it is. Beta particles are electrons that come out of the nucleus when a neutron becomes a proton. Oh yeah. Say it again. A beta particle is an electron coming out of the nucleus when a neutron becomes a proton. And guys, if you understand what you're writing down, this should sound like science fiction. So what is a beta particle? It is an electron. But now, guys, you should be thinking to yourself, well, where does it come from? Answer, the nucleus. Wait, I didn't think there were any electrons in the nucleus. There aren't. There are no electrons in the nucleus. But guys, it turns out that electrons can come out of the nucleus. Wait, they aren't in there. I know, but it happens. So guys, electrons can come out of the nucleus, and this happens when neutrons magically turn into protons. So guys, imagine that you're a neutron and you're hanging out in the nucleus doing your neutron dance, holding the nucleus together, pulling the protons together, and you're doing your neutron dance, and all of a sudden you go, and you turn into a proton, and shooting out of your side goes an electron. That's beta decay. It is a little, for a moment you're naked. Go ahead.
So, does uranium do like beta decay until it's like partially stable and then go into...
Boom! Jeff, that's brilliant. So guys, did you hear Jeff's question? He's like, does it do this a little bit and then that a little bit? And I'm going to show you the answer to that. It's fascinating. Oh, I love that you're doing that because that's closer. I'm going to table your question for a minute and I'm going to show you in a second and you're going to love it. It's crazy. So, guys, this is really what's going on. Neutrons can magically turn into protons, and when they do, they release an electron. But guys, don't have the misconception that a neutron is a proton and an electron stuck together, and if the electron comes out, you're left with the proton. That's not the case. But neutrons can magically become protons, and when they do, electrons come out. Now guys, these electrons are scooting along. We already know that electrons are small, but they're also very high energy. How high energy are they? They can go through my hand, huh? Oh. So guys, let me give you the rule of thumb. The rule of thumb is this. Z goes up by 1 and A stays the same. So guys, in a similar fashion to what we did previously, let's make that make sense. So again, don't write the question, but do write down the answer. So guys, the question is this. What happens to iodine 127 when it undergoes beta decay? So here's what we're going to do. Write down iodine. Big old I. Now gang, iodine is over here. It is element number 53, and its mass is 127. The question is this. What happens when it goes through beta decay? And notice how we write a beta particle. Again, draw your 3 circles representing the nuclei of the atoms. But guys, notice, do not put protons and neutrons in the right-hand circle. How come? Because it's an electron. Just saying. Are you good? Okay, so guys, let's fill this in. So how many protons in iodine? 53. How many neutrons? Do the subtraction. 74. Now guys, this is where this gets interesting. Because now that we're going through beta decay, we release one of these. And again, what is that? It's an electron. But gang, when this happens, a neutron becomes a proton. So a neutron becomes a proton. So how many protons do we now have? We now have 54 protons. Remember, a neutron became a proton. So one of these neutrons became a proton. So protons go up to 54. What happens to neutrons? Down to 73. Now guys, this is where this gets interesting because look at what we've now got. This ain't iodine anymore, right? What is it? It's element 54, which is xenon. But now, gang, do the math. 54 plus 73, guess what that is? Still 127. So guys, again, make the connection. Z went up by 1 and A remained the same. Huh? Oh, yeah. Yeah.
So with like radiation, like when they use to kill cancer and
Yeah.
stuff,
Mm-hmm.
do they use this?
No, so that's a great question. So when they use radiation to kill cancers, even beta particles don't have enough energy. Because that's really what you're doing. All the radiation is a way to get energy into cells to kill them. And so even beta particles don't transfer enough energy to kill cells. So it's at that point that you need to start using higher energy sources like X-rays and gamma rays and things like that. And that's when you end up with transferring enough energy that you can do it.
So it's not directly radiation that they're using, but it's just high concentrated energy.
Yes, but radiation is highly concentrated energy. Yeah. You guys good on beta decay? Okay, so let's go back. I need to glove up again. So guys, here's what we've got. And let me zoom out before we get into this. All right, so here's where we're at, guys. Okay, I'm going to try to do this with one glove. All right, so gang, what do we call this? Background radiation. This guy is going through alpha decay, full irradiation. Now when I do this, why does it slow down? Where are the alpha particles going? Stuck in my hand. What's getting through? The beta particles, the small high energy electrons, they have enough energy that they get through my hand. So guys, the question now is can we stop the beta particles? And the answer is yes, but it takes a sheet of lead. I'll turn it this way so you can see. So, guys, let's play the game again. Background, full crazy, minus the alpha. But now, guys, listen. So when I'm going to go down here, and I'm going to shield the Geiger counter from the uranium with the lead. Now, remember background, right? Okay, so here we go. Did it slow down? Slowed down, right? So it slowed down because the beta particles are now not getting through. Guys, where are the beta particles stopping? In the lead. So alpha is stopping in my hand, beta is stopping in the lead. But is something still getting through? Faster than background. And guys, what has to be true of the stuff that's even getting through the lead? Even smaller and higher energy. And guys, this is weird, but this is so small and high energy that it isn't even a thing. It's called gamma decay. I know.
So the fire department freaks out that you have
I know, right?
like all these other things,
Yeah.
but not a sheet of lead.
Oh, lead's easy. I mean, that's, so long as you don't lick it, you're okay. Yeah. I'm more concerned about the uranium, but they haven't taken it from me yet, so let's just go with it.
Keyword yet. So do you just have to glove up because it'll like burn you or what?
Oh, no, I glove up because, I mean, that's rock, right? And you get dust on you, which is uranium. And then I'm going to have lunch, and you can't wash up well enough to get this stuff off completely. One day, no big deal, but as long as my career's been, I'd rather be careful. So guys, gamma decay is interesting. It is not even a thing. It's energy. Guys, gamma radiation is not a particle. It's energy. You can think of it as being really, really high energy light. But because gamma radiation is not a particle, the nucleus of the atom does not change. The atomic number or the atomic mass does not change. So if that's the case, and if these nuclei are moving towards stability, what function does gamma decay play? And guys, the answer is gone. Guys, the answer is actually this. So when when a nucleus goes through gamma decay, I don't know where this went. Here we go. So guys, when a nucleus goes through gamma decay, it is actually a relaxation process that follows alpha or beta decay. So guys, when you go through alpha decay or beta decay, that creates stress. You can think about the nucleus wiggling. And it wants to release that energy. And when it does, it releases that energy in the form of gamma decay. So guys, you will never have gamma radiation without an alpha or beta process happening first. So it's literally the relaxation process that comes after alpha or beta. How you guys doing? Alpha, beta, gamma? Can we answer Jeff's question now? Okay. So guys, Jeff asked this question. I took off my glove too early. So guys, Jeff asked the question, how did you ask it? I don't even want to try. Okay, well, so guys, let's talk about this then. If the uranium inside of this chunk of uranium is going through alpha and beta and gamma decay, how does all this fit together? And guys, the answer is really fascinating. The answer is actually this. Don't write it down. This won't be on the test. This is just fascinating, so let's talk about it. Guys, this is actually a representation of the life story of a uranium atom. So what's on the y-axis now? Atomic number. So up here, protons, up here is element number 92, which is uranium. Now guys, on the x-axis, it is mass. Not neutrons, but mass. So guys, this then is how this goes. These nuclei actually start as uranium atoms with a mass of 238. And then they go through this kind of decay, which is what kind of decay? Alpha decay, and it goes woohoo! And its mass goes down by 4, and its atomic number goes down by 2, and it becomes element 90, which is what? I don't know. What is element 90? Thorium? Then guys, look at what happens now. The thorium goes through this kind of decay. What's that? Beta decay. Notice that its mass doesn't change and its atomic number goes up by 1, and then it goes through that kind of decay again and its mass doesn't change and its atomic number goes back up by 1, and what does it turn back into? Uranium, but now its mass is 234. Then it goes alpha, 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 alpha. Each time its mass goes down by 4, its atomic number goes down by 2, and it ends up all the way down here at element 82, which is what? Lead, with a mass of 214. Then it goes beta, beta, and it turns into 84, which is what? I don't know. Polonium? Polonium. Then it goes alpha again, down to lead, beta, beta, back up to polonium, then woohoo, down one more alpha to lead with a mass of 206, and that's the end of the story.
So how do we still have uranium?
That's the interesting part, because not all of this happens spontaneously. Inside this rock, there are atoms at every point on this path. Some of these atoms are already down here. Some of these atoms haven't even started the journey yet. And there are some atoms that are stuck at each point along the way. Because remember, this just happens randomly. And so some of them have done this, some of them haven't, and some of them are ever. And that explains why we get alpha and beta decay out of this thing, because they're at every point along the road. So now that brings up an interesting question. How long does this take? And the answer is actually right here. I covered it up, and that's what we're going to talk about in a couple days, is how long this takes. And the answer is some of these processes take milliseconds, and some of them take billions of years. And we're going to look at those time frames in a couple days. So do you get the idea? Yeah? Next. Yeah. It's done. Yeah, because remember, let's tie this all the way back to what we did with the stability thing, right? So why did they do this in the first place? To become stable. So radioactivity is a movement towards stability, and when they get down here, it's game over. This is no longer radioactive. But everything else along the way is radioactive. Yeah?
Oh, so because it gets to lead.
Yep.
But 214, so that's it's radioactive because the ratio's off.
Correct. Yeah, it doesn't
It
have...
goes up, down, up,
There you go. And then it gets to this ratio that is stable, and then it's done. Yeah. You like it? Not bad, right? So, guys, what then was this? Jeff, did that get to your question?
Yeah.
Is that interesting, if nothing else? So, guys, these then are the things that you've got to be able to do in homework today. Do not write this down, just watch. So guys, in homework today, you are going to be doing things like this. So let me show you how to play the game, then I'll give you your homework. So guys, it goes like this. You are going to be asked to identify types of radiation, and you're going to be asked to identify products. So guys, do this with me. Remember the rules of thumb. Alpha decay, the atomic number goes down by 2, the mass goes down by 4. Beta decay, the mass stays the same, and the atomic number goes up by 1. So guys, look what's going on. Here, xenon 54 becomes cesium 55, so the atomic number went up by 1. Is this alpha or beta? Beta. So all you're going to do is write down beta. That's it. But then, how do we represent a beta particle? Like that. Is that okay? Now watch this one. Bottom number goes down by 2, top number goes down by 4. Alpha or beta? Alpha. And so we represent an alpha particle. Huh? Now what about this? What kind of particle is that? Alpha. Now we've got to figure out the product. So the bottom number goes down by 2. The top number goes down by 4. And that would be thorium-234. You get the idea? Okay, now what about this, guys? Where's gamma? Why isn't there a gamma? Doesn't change the nucleus, right? And it could be. These may or may not give off gamma, but we are not going to, there isn't this to do for gamma. So guys, you could also see it like this. So it says radon 222 goes through alpha decay. So there's radon 222. If that goes through alpha decay, the top number goes, or the bottom number goes down by 2, the top number goes down by 4, or beta decay. And if that happens, the bottom number goes up by 1, the top number stays the same. You get the idea? Okay. So, guys, this homework looks like a lot because it is. This is a big assignment. It is double-sided. You are going to need another sheet of paper to do it. Guys, we will grade this on Thursday, and then we are going to be watching movies and writing response papers for the next 2 days. I think you're going to find it interesting.
Why is radiation like so bad for you?
That's, ooh, hold on.
Thank you.
Mm-hmm. You have a donut. No. Jaden and I are trying to lose weight.
Yeah.
Hey guys, there's a really interesting question on the table. Actually, the answer is because these particles, alpha and beta particles, have an ability to transfer energy. And when that energy gets inside of our cells, it actually disrupts the function of our cells, specifically disrupting our DNA. And when that happens, these little factories inside of us that make proteins and things like that get short-circuited, and they start creating cancerous cells. Then the question becomes, why then do we use radiation to kill cancer? And the answer is because we can actually deliver so much energy that it doesn't short-circuit the cell, it kills the cell. And that's what we're trying to do. So, yeah.
Do you use radiation to like delete certain parts of the DNA strand?
Oh, yeah. Yeah, yeah.
Can you make it specific and not read through all the DNA?
They are, so I have a friend up at Huntsman Cancer who's actually a doctor and a PhD physicist that's working on that very stuff. And and that's what he does, is figuring out how to focus, if you will, those energies.
Is there, my nephew has my tongue,
repetitions of a certain
Yeah,
thing.
right. Best way to do it because it tends to still be a pretty blunt instrument. I would suspect there's better ways to do it.
I think they're looking at finding a virus in PPD.
There you go. Yeah, Max.
Can we speed up radioactive decay?
That is a brilliant question, and the answer is yes, and we're trying to do that. These are what are called breeder reactors. It's one of the things that you're going to see in the Bill Nye video on Thursday. Is the problem with nuclear power plants isn't that they pollute. The problem is the radioactive waste that's left when it's done. And if we could find a way to get it to speed up the radioactive processes, we could then store it. And so what they do is they take this radioactive material and they bombard it with neutrons, not enough to get it to become a bomb, but they bombard it with neutrons, and that speeds up the decay processes in the hopes of actually closing down the amount of time that it takes for them to decay to lead.
Why don't we just shoot it into the sun?
That's a great, and they're going to talk about that in the video. Here's why. We have sent about 200 space shuttle missions into space, and 2 of them have exploded. So we have about a 1% failure rate on sending things into space. If that space shuttle had been packed with a couple tons of radioactive material, it'd be game over. So until we can do that perfect, yeah, because you're right, if we could just dump all this in the sun, it'd be no problem. But the problem is getting it there, right? Yeah, it would, but to get it there safely is a whole nother game. So we're working on it. Oh yeah.
Can I get a drink?
Why don't you just take your stuff and go?